small micron-sized bits in mucin layers, hydrogels, if you wish, at different pH, at pH 7, at pH 4, and at pH 2. And what they see at pH 2 is a very interesting picture. So they have particles, as you see here, which are Gaussian, in displacements, and there is a subset of particles which are very Laplacian in PDF. So they have a population splitting, if you wish, and these two sets of particles kind of equilibrate themselves in the layer of mucin. And at pH equals 2, actually, as macro-rheological measurements show, this layer of mucin is a very complicated layer because it has regions of very dense mucin and very dilute mucin. So some of the particles, as you see here, can be trapped in the layers of dense polymer network, and some can be kind of diffused almost freely in a dilute polymer network. So I got the data from Caroline, and we did some analysis on this. Here are some results very shortly. So we got our TAMSDs, our favorite quantifiers. And as you see here, each of the trajectory, for instance, blue is pH 2. Each of the blue trajectories is very different in a transport, for instance. So we have a very, very broad spread of trajectories. This is the first indicator of our non-ergodicity. So each trajectory behaves differently. This we quantify in terms of the EB parameter, which is for the blue data very, very high. So the value of parameter is actually the degree of non-ergodicity, if you wish. This asymptote is our Brownian motion, the most ergodic process, if you wish. Well, for pH 7, for instance, nothing special happens. Our EB parameter is very close to the Brownian motion, and the trajectories, these purple ones, are very, very little spread. So we have, but all of them actually are not equal to the MSD, which you see here on the inside. So TMSDs are not equal to the MSDs for all the pH values. What is interesting for this data set, and also for the other sets I will show you, is the fact that once I compute the transport coefficient, this K alpha, and plot them versus the transport exponent for each of the trajectories. So each dot is a trajectory. You see that there is a huge correlation at all three pH values. So transport coefficients are correlated with the exponent. So these are slow trajectories, and up there are high trajectories in terms of exponent and diffusivity. And this population splitting of blue trajectories you also instantly see, because these are two subpopulations we observe. So at pH 2, the diffusion is most non-ergodic. We have also a tool in our arsenal, so-called Bayesian model inference analysis, which we apply to this data to understand which kind of diffusion models are realized. So these three columns you see at pH 7, pH 4, and pH 2. So at pH 7, nothing special happens. Red is Brownian motion. So most of the data are Brownian motion. And this diffusivity we only see for a couple of trajectories. For pH 4, where diffusion is becoming slower and anomalously subdiffused, we have most of the trajectories FBM, fractional Brownian motion. And for the most interesting case of pH 2, we not only have FBM, this blue data here, in terms of models. On the horizontal scale, this is the number of each of the traces. But in terms of the exponent, we have a splitting of the exponents into two subpopulations. So there is a slow subpopulation and a quick subpopulation. This is this splitting of trajectories I have shown you previously. The next quantifier is clearly the PDF, and here you don't expect any Gaussianity, and indeed, particularly at pH 2, which is this blue data, you see this cusp at the zero displacement of the particle. So it's possible to fit these PDFs as I did, either with a stretch Gaussian or compressed exponential, to extract this non-Gaussianity exponent delta, if you wish, for each of the pH values, as I did here. And the point is to understand as we go from left to right, as you see, the time displacement changes. So the point is to understand how the width of these distributions actually grow with time. And this is actually what I did. So on this slide, you see how the width of the PDFs grow with the time lag, if you wish, for all three pH. And instantly you see the pH 4 set, which is more subdiffused, and also producing here rather subdiffusive behavior, while two other pH are producing rather well, close to Gauss, close to linear behavior with the exponents of close to 1, if you wish. So these exponents are actually consistent with the TMSD exponents we obtained previously. And overall, this sort of supports our idea of self-consistent diffusion law for these data at different timescales. And lastly, the velocity autocorrelation function is also consistent with this picture. So we have subdiffusive behavior for pH 4, this cusp, this kind of dip at short times is a characteristic of subdiffusion, while two other pH give you nearly Brownian behavior, where this would have been a drop to 0 and the correlation function would stay 0. So we have kind of an overall kind of very quantitative picture of diffusion of these particles in mucus gels. And our idea of continuous time random walk, which would be attributable to the fact that particles are being trapped in the regions of high concentration of polymers and then producing some sort of trapping events, is not working here, because once we compute here the magnitudes of TMSD, which are for subdiffusive continuous time random walk, should be a rather sensitive function of the trajectory length T. We don't see this effect, so we don't see this dependence on the trajectory length. So we can exclude continuous time random walk as a model and rather propose a model of kind of heterogeneous environment, which is at pH 7, as you see here, all the PDFs are given similar widths. So all the particles, in a way, build a very uniform ensemble of particles. While at pH 2 on the left here, you have the width of each PDF, which is very strongly variable function as a function of the particle number. So ensemble of particles is very heterogeneous, and this heterogeneity, being sampled by particles, is actually a cause of non-ergodic and non-Gaussian diffusion, if you wish, for this set of data. Next set of data, which is done in close collaboration with biological group at the Poznan University, Professor Pita, is this diffusion of so-called dictyostelium discoideum, these amoeba cells, which are diffusing in 2D, as you hopefully see on this video. These are the trajectories of those cells. The cells themselves are very homogeneous in size, but very variable in shape. And this, again, will manifest itself, as you'll see, in the properties of diffusion we are observing. Kinematically, these cells kind of run straight for a couple of minutes, and then they, due to the internal clock incorporated in cells, they turn on arbitrary angles and continue their active motion. And this motion is actually being triggered by action polymerization. So the cells kind of grow and age in front of them due to active polymerization of these pseudopodia protrusions, while on the back of the cells, due to depolymerization of actin, the cell sort of repeals from the surface. And this kind of rolling motion of the cell is how the cell propagates for these amoeba cells, as well as for a number of other kind of propulsive cells. A couple of words about the data. So they were recorded for up to several hours with a time step of about 20 seconds. And what we see here are all the trajectories superimposed on one another. The cell density is not that high. We just see plenty of trajectories on one image. And the trajectories are dominated, as you see here on the bottom, by rather short trajectories. And this also has implications on the diffusion. So once we do our famous TMSD, this is the red curves here, you see that each of the cell produces its own trajectory. So there is a spread which is as large in these trajectories. And the mean TMSD, this blue curve, and the mean MSD, this green curve, hopefully it's visible, are not really the same in magnitude and also not the same in exponent. So this cell-to-cell variability gives rise to non-ergodicity also for this sort of thing. Here on the right, I plot the initial magnitude of the TMSD, if you wish, the transport coefficient for each of the trajectories, the dot with each of the 1,000 trajectories we have. And what we instantly observe is that longer trajectories are becoming progressively slower. And this is actually not surprising. This is our aging effect, when the TMSD not only spread among the trajectories, but is also a function of the trajectory length here, as you see here. So this is kind of aging behavior because longer trajectories are becoming slower and slower with time. However, the motion is actively driven, as you see the exponents which I computed are actually slightly above units, at least at the beginning. And then later, as a trajectory becomes kind of slower and more subdiffuses, the exponents drop. But the statistics here on the end is not that great, actually. The point of this image is to present you cell-to-cell variability, how much different diffusion can be depending on each given amoeba cell. This plot illustrates how the distribution of TMSDs, which is quantified by this kind of normalized variable, spreads in time. So we have a rather localized distribution at the beginning of the measurement and very spread distribution in the end of the measurement. Again, due to first cell-to-cell variability, and second due to kind of lower irreproducibility of signals towards the end of the trajectories. Another interesting feature is the fact that if I do my transport coefficient for each of the TMSDs, again, the dot is each of the trajectories, versus the TMSD exponent, I see very clear anti-correlations compared to the mutant data I've shown previously. And so this way you have amoebas which are very high in exponent and very slow in diffusivity, and vice versa. Very slow in exponent, but very high in diffusivity. And for me, this is a very clear indication of some sort of fitness of this population, because if you imagine in an ensemble of amoebas which are looking for food or escape some kind of harsh environments, if you wish, they need to be all different. And this way, not the whole colony will die, but only some part of the colony, and another will survive. So this sort of variability in transport coefficients, which we observe here, and anti-correlation is the fact that these cells use energy available to them, either to propel themselves in terms of exponent or in terms of diffusivity. This is how I see it kind of biological. But the main implication is fitness. This variability helps colony of cells to be kind of survival for longer times. The PDF, clearly, you can do the same trick as I did. You can do the non-Gaussian fitting of the PDF. So I split it the X and Y direction, as you see here. And you can compute actually this delta exponent, which is rather close to unity here. So the distributions, as you see, do not look Gaussian at all. They look rather Laplacian. And what was surprising to me is that the width of the distribution, once I plotted versus the time shift, gives me a very clear scaling exponent, which is very close to the scaling of the MSD I had before. So this kind of supports our diffusion law for the MSD and for the width of those PDS distribution. And due to this, I can have my rescaled space-time variable to incorporate diffusion this kind of exponent into the variable. And this way, I can present all the PDFs on this plot at different space and time kind of values as one universal master curve. And as you see, they superimpose. And this very kind of non-intuitive for the noisiness of data we are dealing with. So I'm very happy to have this kind of universal diffusion law behind. Correlation function is, because this is an active motion, the correlation function doesn't drop below zero. It stays above zero. And the correlation function actually looks very similar to the FBM correlation function shown here on the bottom, where the normalized function drops to some certain value and then kind of approaches zero slowly. You can also compute the velocities of these amoeba cells, and the velocities is not becoming maximal Boltzmann, but it has rather longer tail, known actually for a number of other propulsive cells. So this is kind of gamma distribution for the velocities of these particles. Now let me move to the certain last part where we deal with diffusion of these so-called doxorubicin molecules in silicon nanoslits. So this illustrated image shows you silicon nanoparticles which are nanoporous and incorporate certain drugs. This is actually the procedure which is being used for several substances in recent years. Let me give you a short introduction to these doxorubicins. This is a ubiquitous drug, anti-cancer drug, which is used to treat several cancer types like breast, stomach, lung cancer. It has, however, several side effects like red devil effect, red skin effect, and heart failure. So people use this drug for many decades, but still, due to this side effect, it should be processed and delivered in a certain way. And one of these ways is actually to put this drug into, in this case, porous silicon nanoparticles with some pores, which then allow drug to exit. You can control the diameter of these pores and, in a way, control the concentration of drug in the blood, if you wish. And what is important is the release of the doxorubicin particle from these particles is pH dependent. So at smaller pH, you have a substantial release within 24 hours, while at larger, at physiological pH 7, you have a very slow release. And this is important because cancer cells are known to have somewhat smaller pH. So the idea is to deliver these rather toxic drugs namely into cancer cells and let them kind of act there, not poisoning healthy cells. And this is what silicon nanoparticles actually allow to do. That's why we kind of study this diffusion of doxorubicin on silicon nanoslit in our case. So this is a third set of data, as I said, coming from the collaboration of Professor Metzler with Imperial College London. We have now not so many, 50 very long all-atom trajectories from supercomputer simulations. And our goal is to examine what kind of diffusion model can be behind this data. Very shortly, so this doxorubicin in a planar slit of silica diffuses like a two-step process. It has an adsorption mode and a diffusion mode, quick jumping processes. So in adsorption sites, it has kind of 4 conformations, but we are mostly interested in the diffusion mode. Again, going to the TMSD analysis, we have our MSD here, the gray or black curve, and the TMSD, our blue curves, which are not equal to one another, again, indicating breaking of ergodicity. In the inside, you have the exponents, which are varying, very funny, actually, in opposite direction along the trajectory. I don't have much time to go into the details, but what is important is that we instantly have an indication that continuous time random walk is not the model that would be favorable for this data, because
Andrei, about 2 minutes to go, more or less.
Okay. So continuous time random walk is not the model we want to attribute to this data, although some of the properties are actually favoring continuous time random walk. What I want to say is that fractional Brownian motion is more attributable, for instance, for the correlation function, where we superimpose our another simulation data, and you see that doxorubicin actually is behaving like FBM in the subdiffusion region. So I'm finishing saying that our doxorubicin set has actually features of both FBM and continuous time random walk, actually asking us as theoreticians to produce these hybrid processes I've shown you in the beginning of the talk. And with this, I want to finish saying that in all these three data sets I've shown you, we have seen non-Gaussian, non-ergodic agent diffusion with some variability of diffusivities. However, this is just a start. We want to understand more. We want to see some systematic data where some physical parameters which are important, like concentration of mucin or amoeboidal activity or slit thickness, are being changed. So this way we construct kind of a multi-dimensional map from our model analysis. And this way we can understand the features of diffusion and the interactions, the complexity of the system, and gain some new insight into the behavior of this physical system. So with this, I am finishing. Thank you very much for your attention. And these are the collaborators, particularly Professor Metzler and Professor Bitter, who contributed a lot to these studies. Thank you very much.
Thank you very much indeed for your really impressive talk with many formula, but also many examples related to the formula. Okay, right now, yes, let's clap the hands.
Thank you.
And right now, the paper is open for discussion. Yes, Roland Winkler, Professor Winkler from Forschungszentrum Jülich. Bitte sehr.
Hello, Andre. Hi, Andre, you hear me? Oh.
A little bit, yes.
Sorry, I have to go on the stage. Hello, Andre, is this better now? Andre?
Yes.
You hear me? Okay. I wonder about your definition of ergodicity, comparing your, let's say, your MSD and your time-averaged MSD. I have the feeling that your time-averaged MSD contains or measures to some extent the correlations in the system. Means you're looking at intervals of MSDs, of intervals of length delta. You average over the time interval in between, but the samples you're averaging over are not independent. So they contain a certain correlations in the dynamics of the particles, and they reflect that. And that gives I can understand then that there's a difference between the MSD and your time-averaged MSD. So my question is, in principle, first of all, what is your definition of ergodicity?
Well, as I said in the very beginning, so we are kind of taken a very simple definition. So once the MSD and TMSDs for each time are not equal in magnitude or in exponent, we are calling this system non-ergodic. We are not going to this mathematical definition of mixing or strong mixing or weak mixing. People like Penrose and Leibowitz were kind of telling us like 40 years ago, simply because our often biological data are very sparse. So we don't have much of data. So we cannot kind of have a very complex quantifier to understand this phenomenon. And on the other hand, our MSD and TMSD is rather straightforward. And if the process is indeed ergodic, like Brownian motion, or like, as you saw, mucin gels at pH 7, these two quantities do not give you much of difference, for instance, as you see here, for the purple curve. But once the system is very complex, they instantly show you the differences. And this is what, in addition to the EB parameter clearly, which quantifies by its value how much spread you have in the TMSD. So not only the magnitude and exponent, in addition our EB parameter, which is a higher moment of the distribution of the TMSD, if you wish, is another kind of support for the data.
I accept that. Of course, if you talk about biological systems, looking at A and B, which is supposedly the same thing, you can measure different effects because of some heterogeneities in there. No problem. We can discuss it another time maybe. But I still think what your TMSD measures is some correlations in the data. And you probably can look at a different function which expresses differences in the correlation in the data. I accept that you get a significant difference in the numbers there, but whether this is a good measure for saying it's ergodic or non-ergodic, that I'm not so sure of. But let's discuss that in more detail in a more private discussions when we meet or
Thank you.
Yeah. Thanks, Andre. It was very interesting.
Thanks a lot. Okay, are there any other questions to our distinguished speaker? Okay, I've got one, namely that you emphasize the role of pH in the non-ergodic systems. Did you find some systematic relation between this measure, which is the pH, which is, for example, equal to 7 for neutral systems, and of course for basic and acidic systems it's a little bit different, less than 7 or bigger than 7, but is there any really systematic measure of the non-ergosity in terms of the pH for the systems you examined?
For instance, for the mucin data you see here on the slide, you need to understand kind of the complexity of interactions in the polymer network, which is there, because these mucin polymers have several types of physical chemical interactions which can be pH specific. In addition, you can cover particles, which are these small polystyrene with certain substances to screen or not allow them to interact with the network. So, on the microscopic scale there is complexity, but also on the macroscopic scale, due to this solidification of the network at pH 7, for instance, for the mucin data, you have heterogeneity. And I think my message here is that pH delivers you this heterogeneity degree. And all particles are not diffusing in the same environment. This is the point. So each of them samples kind of different structures of these rather non-uniform environments.
Right.
And now, having worked with the data for a while, I understand now that sampling mechanisms and how actually the data are being presented to you, whether they are cut, how long are the data, what is the minimal length of the trajectory people consider, what is the maximal length of the trajectory, is way more important for the results. So you need to, like Leo Tolstoy was saying, every family is unhappy in its own way. Every data set is unhappy in its own way. And you need to understand, much of the details to make the really kind of good statements about ergodicity, as Professor Winkler was asking. And that's why, I'm dealing with the data to really understand how the concept of theory can be useful. But the data is sort of dirty. You need to understand how they are taken first.
Maybe do you attribute this solidification in the network you mentioned to the number of the H bonds they may be created? They can also be, of course...
Exactly. There are several bonds there, hydrophobic interaction, disulfide bonds, as well as several chemical interactions. And so I'm not an expert there. PhD thesis written on the subject. And it's not very, mucin network is one of the most complex networks actually in the body, because the polymers themselves are the longest you can see in the body. There are 100 millions of Dalton long. This is very,
Yes,
very long.
that's true.
And they are hierarchically structured on different scales. So this is an very, very kind of brushy, but also density of this network is changing with time, and the hydrogel loses water. Plenty of effects are being mixed together.
Yeah, thank you, Andrei. Of course, yeah, I
Thank
know
you very
that
much.
you also exchanged some ideas with Dr. Natalia Kruszewska, because she published also a paper in Membranes. Yes, it is this fact, and you are aware of this fact, and you've exchanged some of, let's say, fresh ideas about your paper and her paper. This is what I simply discovered while talking to the people from my group.
I see. Yes.
Yes, thank you. Okay,
Thank you very much, Adam.
Yeah. Okay, this is the closing ceremony of thanking you once again by clapping our hands. Thank you very much indeed.
Thank you. Thank you.
Bye. Thanks a lot.
Jeszcze może z małą informacją, ponieważ